The most advanced technologies in the world are built on the most unstable parts of the supply chain. 75% of the world's cobalt comes from the Democratic Republic of the Congo, much of it pulled from hand-dug tunnels as deep as 40 meters with no structural support. Every smartphone, every electric vehicle battery depends on this, and the system that keeps it running is engineered so you never see how. Mining risk is defined by two dimensions: the nature of the hazard and the structure of labor. Acute hazards, such as tunnel collapse or sudden asphyxiation, occur in environments where physical conditions are unstable and support systems are absent. Chronic hazards, including long-term dust inhalation and cumulative exposure to toxic metals, build over time and are rarely tracked by formal health monitoring. In the context of cobalt extraction in the Democratic Republic of the Congo, the distinction between industrial and artisanal mining is central. Industrial operations are capital-intensive, mechanized, and typically subject to regulatory oversight. Artisanal and small-scale mining relies on hand tools, informal labor, and minimal engineering controls. Field surveys by the International Finance Corporation, the World Bank, and other agencies consistently find that hand-dug artisanal cobalt shafts in the Democratic Republic of the Congo range from 15 to 40 meters deep. This depth band is significant. It pushes miners below the threshold for natural ventilation or safe egress, while remaining shallow enough to be excavated without machinery. Within these shafts, roof support is improvised or absent, and the risk of collapse or suffocation is persistent. Artisanal and small-scale mining accounted for 9 to 11% of Democratic Republic of the Congo cobalt output in 2020, a non-trivial share in a market that supplies 3/4 of the world's cobalt. Labor classification further divides formal, regulated employment, where safety standards, insurance, and contracts are present, from informal arrangements, where miners operate outside legal frameworks and without health protections. In the artisanal sector, the absence of regulatory enforcement means that exposure to acute and chronic hazards is routine, not exceptional. The operational environment is defined by cost pressure, subcontracting, and the need to extract maximum volume with minimal investment in safety. This architecture is not a byproduct of poverty or oversight. It is a functional feature of the supply chain. Risk is transferred to the point of extraction, embedded in the economics of cheap, flexible labor. The modern supply chain does not eliminate risk. It relocates it. Cobalt moves through a 4-layer supply chain, each stage defined by its own technical demands and barriers to entry. The first layer is extraction, anchored almost entirely in the Katanga copper belt of the Democratic Republic of the Congo. Here, the geology dictates that most of the world's cobalt can only be accessed in this narrow region, creating a geographic lock that shapes the entire chain. Material leaves the ground as raw ore, often produced by both industrial mines and artisanal shafts operating side by side. The second layer is primary processing. At this stage, ore is crushed, washed, and concentrated, either in basic local facilities or in larger industrial plants. Processing removes some impurities, but leaves the material in a form that still requires advanced refining. The capital cost for even a modest processing plant runs into the tens of millions of dollars, keeping most artisanal output dependent on simple, low-cost methods. The third layer is refining and smelting. This is where cobalt is converted into high-purity metal, or sulfate suitable for batteries and electronics. The capital intensity here is significant. A new refinery costs over $500 million to build, and most global capacity is concentrated in China and Europe. Only a handful of firms operate at this scale, and access to this layer is tightly controlled by both capital and technology. The final layer is integration. Refined cobalt enters global manufacturing networks, where it is blended into battery cathodes, electronic components, and end-use products. At this point, the physical trace of extraction risk disappears. the material is indistinguishable from any other input, and the original hazards are no longer visible in the finished product. Each handoff in this chain is both a technical and economic filter, concentrating risk at the bottom and value at the top. The structure ensures that hazardous extraction environments remain a persistent feature, while downstream actors operate in high-value, low-risk contexts. At the mine gate, cobalt sells for between $35 and $45 per kilogram. This is the baseline, the price of raw material extracted under the highest risk, where safety investments are minimal and hazard is routine. Once ore leaves the ground, the cost ladder begins to climb. Primary processing, crushing, washing, and concentration adds another $7 to $9 per kilogram. This stage is capital-intensive enough to exclude most artisanal operators, but margins remain slim, and risk exposure is still pronounced. Refining is the next escalation. Here, cobalt is purified in large-scale facilities, often overseas, with costs rising by an additional $12 to $15 per kilogram. At this point, the technical barriers are high, and only a handful of firms control access. The material is transformed into battery-grade sulfate or metal, and the value captured at this stage is no longer tied to extraction risk, but to capital, technology, and market access. The finished product, cobalt ready for battery cathodes or electronics, sells for $30 to $35 per kilogram on spot markets, with long-term contracts locking in prices just below that. Margins for battery manufacturers and traders are layered on top, often reaching 20 to 30%. By this stage, exposure to collapse, dust, and acute hazard is remote. The economic structure ensures that the lowest price and the greatest risk are concentrated at the extraction tier, while each downstream step absorbs less risk, but captures more value. This asymmetry is not incidental. It is the mechanism that preserves hazardous extraction as the foundation of the system. The modern supply chain does not eliminate risk, it relocates it. Global battery demand continues to climb, driven by electric vehicles and portable electronics. This appetite for cobalt is not evenly distributed across the map. Roughly 75% of the world's cobalt supply comes from the Democratic Republic of the Congo, anchoring the entire supply chain to a single region. The concentration is not just geological, but structural. No other area offers the same combination of ore grade, scale, and low-cost extraction. As a result, manufacturers and traders face a geographic lock-in that shapes every downstream decision. To meet demand, battery firms rely on a web of subcontractors and intermediaries who operate at the extraction tier. These arrangements externalize risk by pushing hazardous work onto informal diggers, who are not employees but day laborers with no contractual protection. The system is reinforced by tolling chains, business models where ore is sold or processed through a series of third parties, each capturing a margin while transferring liability for safety and compliance further down the chain. This structure allows large buyers to secure volume at the lowest possible cost, while distancing themselves from the conditions of extraction. In practice, cost pressure and demand growth ensure that hazardous labor persists. The economic incentive is clear. Safer, mechanized mining would raise extraction costs by 15 to 25%, an increase that few downstream firms are willing to absorb. Subcontracting and geographic dependency create a system where risk is not accidental or marginal. It is a built-in feature, maintained by the need to deliver cheap, high-volume cobalt to the global market. The modern supply chain does not eliminate risk, it relocates it. Traceability in the cobalt supply chain is shaped less by intent than by the mechanics of bulk material flow. As ore leaves artisanal and industrial sites, it is routinely aggregated and blended at local processing hubs. This blending, designed to meet minimum volume and grade thresholds for export, erases the physical markers that could distinguish high-risk origins from regulated sources. Once mixed, cobalt from hand-dug shafts and mechanized pits becomes indistinguishable, and any record of upstream hazard is lost in the process. Certification schemes attempt to impose order on this opacity. Third-party auditors, such as RCS and ITRI, and initiatives like the Fair Cobalt Alliance, have introduced chain-of-custody protocols to trace cobalt from extraction to export. Yet these systems rely on voluntary disclosure and periodic site audits, not on continuous tamper-proof monitoring. The 2025 release of 1,000 tons of traceable artisanal cobalt by the DRC's state agency marks a technical milestone, but it remains an exception. The vast majority of cobalt, especially that routed through informal traders and export houses, enters the global chain without source-level verification. At the refining stage, further aggregation and chemical transformation render any remaining trace of origin invisible. By the time cobalt reaches battery and electronics manufacturers, the physical and informational signals of upstream risk have vanished. Certification bodies operate as institutional actors within this system, but their reach is bounded by the architecture of material flow and the economic incentives to maximize volume. Product transparency at the consumer end does not guarantee supply chain transparency. The modern supply chain does not eliminate risk, it relocates it. System failures in high-risk mining follow recognizable patterns, each with measurable consequences for both human safety and global markets. Three archetypes dominate: tunnel collapse during extraction, dust ignition in primary processing, and smelting fire at the refining stage. Each failure is rooted in the same risk architecture, namely structural shortcuts, cost-driven maintenance gaps, and underinvestment in engineered controls. A documented dust explosion at a metal processing plant in West Virginia revealed airborne concentrations of titanium dust 12 times the recommended safety limit, leading to a catastrophic ignition. In cobalt mining regions, annual reports from the Democratic Republic of the Congo record more than 200 fatal shaft collapses, with chronic dust exposure driving silicosis rates 2 to 3 times the national average among artisanal miners. When a single node in this chain fails, the impact is not contained. Modeling a 10% supply cut in cobalt output from the Democratic Republic of the Congo produces a 15 to 20% surge in global cobalt prices. This elasticity is amplified by the geographic concentration of supply and the inflexibility of downstream manufacturing. A price spike of this magnitude raises battery pack costs by $30 per kilowatt hour and triggers immediate procurement risk for electronics and automotive manufacturers. Spot buyers face margin squeezes, while firms with long-term contracts scramble to renegotiate terms or seek alternative chemistries. The cost of failure is quantified in both human and economic terms. Injury and disability rates rise upstream, while volatility and price shocks propagate downstream. The modern supply chain doesn't eliminate risk, it relocates it. Risk is not an aberration. It is engineered into extraction economics and diffused across every stage of production. As demand for advanced technologies accelerates, invisible exposure remains the baseline cost. The modern supply chain doesn't eliminate risk, it relocates it.